Okay, guys, so we're going to cover parallel battery hookups. So if you have a 12 volt battery, 100 amp hour. Hi, Maggie's. My black lab. So we have two 12 volt 100 milliamp or 100 amp hour batteries. To hook them in parallel, we're going to hook the negatives together, and we're going to hook the positives together. There we go. So that will give us an output of 12 volts, and we'll have 200 amp hour capacity. So that's parallel. So now I'll show you series. Now we're going to hook them in series. This would what you would do for a 24 volt trolling motor. So we have two 12 volt batteries, 100 amp hour. And you want your batteries to be purchased at the same time if you're going to be hooking them up like in parallel. It's always good practice to do that. And then what we're going to do is, so here's the, let's draw out the negative terminals here, positive terminals. Okay. What we're going to do, we're going to put a jumper for series connection. Then our 24 volt trolling motor will hook to here. Our output will be 24 volts at 100 amp hour. When you hook them in series, you gain voltage. So you go from 12 volts to in series, you get 24 volts, but you don't gain anything as far as amp hours. So that's how you would hook it up that way. Now if you had a 36 volt trolling motor, you'd have another 12 volt, say 100 amp hour battery. And then what you do, you move this connection here, but you'd go in to the other negative terminal, and then your output would be the plus here. So you can get rid of that connection there. That would actually be the positive side. So then this would give us 36 volts, but the amp hour is still going to stay the same, 100 amp hour. So that's series and parallel connection. Now I was going to show you here, we got showing how you would jump start your engine if the starting battery went bad. So let's say we have a 24 volt trolling motor. So we have our two 12 volt batteries. They're going to be wired in series. So you're going to have like that going down to your trolling motor. Okay. Now if you need to jump start your trolling motor or your starting battery is dead because of your electronics, bilge pumps, or whatever all you have hooked to that. I mean, you've been fishing for a while, haven't started the engine, it hasn't had a chance to charge, so your battery's dead. So what can you do? And there's been a lot of questions on how you do it. You do not want to hook to here and here. Do not do that. The correct connection can be either of these batteries. You don't have to unhook any wires. Just take your jumper cables, hook only to one of the batteries. Take your jumper cable, minus to minus, and then positive to positive. And then, I probably wait a little bit because naturally, because the one of the it's going to be a higher voltage than that, so it'll naturally. So I'd probably wait like 10 minutes before I try to start. You may get away with being able to start it right away. In most instances, you probably could. But anyway, if it doesn't start on the first try, just give it 10 minutes or whatever to. You actually have current flow naturally into that. To this battery here will effectively would be like a charger and charge this battery up. You get current flow because the voltage is lower here. So say it's down to 10.5 volts, which is pretty low for trying to start it, but this one's up at 12.5. Because the difference in voltage, you're actually going to have current flow, which means it's going to be technically charging this battery. So that's what you would do in that instance. You don't hook, here. Some guys said they hooked it up and they heard pop and it blew the fuse in their engine. It's not good. They hooked to here, they hooked here, and here in the series. Don't want to do that. You want to hook to just one of the batteries, minus plus. And you don't have to remove any jumpers or anything. It's always a good idea to get you a good DMM, digital multimeter. Get them at Radio Shack for next to nothing. And they're easy to use. Just put them on the volts DC scale. Most of them are automatic anymore these days, and so you can actually hook here. You just want to double check things. You make sure you're getting 24 volts. Just hook your digital multimeter from here to here. You should have 24 volts. From here to here you'll have 12. From here to here you'll have 12. So anyway, that kind of covers jump starting your starting battery with one of your trolling motor batteries. Okay, now I'm going to cover something that was brought up in the forum that I was on. I can't remember which one it was, but I'd seen it brought up, and it's a very bad situation. Somebody had made the comment that you need to hook the grounds together on a 24 or 36 volt system. That is not good to do, and I'll show you why. So we have a 36 volt trolling motor. So of course we're going to do a series connection. Should change the color, but anyway, you get the idea. So there's our series connection. So this will be 36 volts. Well, a person had mentioned and actually said, and probably confused some of the guys, that you want to hook your negatives together. Well, what would happen if you hook the negatives together? It's pretty easy to tell what would happen. Basically, you're going to dead short a battery. So if you were to take and hook all these negatives together, you're only going to start to get one hooked up before you see a big arc, and you'll know you have something hooked up wrong. Because if you look here, what have you done? Okay, if you've hooked this negative to this negative here, right, and it has a series connection in there, what's gonna happen? Remember, there's a connection here for the series connection. So now all of a sudden, because that connection's there, this wire here is going to just get hot. I'm telling you, it's going to get smoking hot. Both wires will. They're going to get hot. And it's going to cook this battery. It could possibly explode. Who knows what could happen. But it's not a good scenario. Don't hook the grounds together. I don't know why that suggestion was brought up in the forum. You don't do that. Don't hook the grounds together. So you can see where the problem would happen. Effectively, you're just shorting, in this case here with this wire here, you're directly shorting this battery here. I mean, terminal to terminal, dead short. So you don't do that. Okay, now we're going to take a look at hooking in a 3-bank charger. Typically, if you have a 36 volt trolling motor, you're going to have actually a 4-bank because you got to include your starting battery in there, but just for simplicity, 3-bank charger, 3 batteries for 36 volts on the trolling motor. And so on your 3-bank charger, you're going to have 3 outputs. So one output's going to go to here, and then you're going to have minus and a positive going to there. Your other one, there to there. And then your other port there to there. Now, one thing that's interesting, when you get these chargers, they only have a fuse on the positive side. Internally in the charger, the grounds are isolated from each other. They are isolated in the charger. And I don't know why, but I would think it would be a good idea for the manufacturers to also include a fuse in the ground. And here's my reasoning behind that. I had a friend who had a 3-bank charger, and it violently blew up. After looking through it, it appears that internally, one of the grounds had actually, something happened in the charger. I don't know what happened, but anyway, it caused 2 of the grounds to actually connect. I verified it with an ohm meter, and they were dead short. They, typically they're supposed to be isolated. For some reason, something happened in the charger. Of course, it was all potted and you couldn't really get it open. But with an ohm meter, I could verify that one of the or 2 were actually dead short. Well, we talked about earlier not hooking the negatives together in a series connection. So here's our series connections going down to create our 36 volts. Well, imagine if internally that charger, one of the isolated grounds, they actually connect to each other because of a problem in the charger. Without a fuse here, basically you get current flow all the way back into the charger and then out to the port that the isolation has went away, back out on that ground side, and you've created a dead short. So those wires will get hot. His charger actually smoked, actually burn up the ground wires and stuff. I know the manufacturers don't include a fuse on the ground, but just from a safety aspect, I think it's a good idea. I think manufacturers should include that. It's a standard procedure in the industry I work in, that anytime you take anything to the battery, directly to the battery, if you're not going to take the ground to the chassis, and you take it directly to the battery, the ground is always fused. That's because if that, say for example, this in a car, from the negative terminal on the battery to the chassis came undone, well then guess what? All the current flow is going to be through that ground, and so that's why you want that fuse in there. And I would rate that fuse, if you were going to do it and you were concerned about it, make it the same rating fuse as what's in the positive lead, and you'll be safe there. That way, if anything internally happens inside that charger where all of a sudden your isolation between grounds goes bad, that it'll immediately pop that fuse. So I don't know why the industry doesn't do it. For the most part, all the chargers I've seen, they don't include a fuse on the ground side for multiple bank chargers. I think it should be a requirement. You never know what might happen. I think it's something I would add in anyway. I don't happen to have a 24 volt, so I don't really have to worry about it. But to me, it's a big safety issue. So it's really up to you if you want to do that or not. But me, if I had a boat that I had 36 volt trolling motor and my starting battery and stuff, I'd be putting fuses in the negative side as well, just in case that charger ever lost its isolation between grounds. So anyway, just kind of want to go over that, or at least my thoughts. So, okay guys, I thought I'd also cover why the manufacturers, 12, 24, 36, usually that's associated with, more voltage, more power. That's true. I mean, higher voltage, and usually it's higher power, but there's a reason why they go to 36 volts, and it all has to do with wire gauge. Imagine if you had a 12 volt, 101 pound thrust trolling motor. That sucker on high, who knows? I mean, I'm just guesstimating. Let's say it's going to pull 80 amps at 12 volts. That means you're going to have to go with like a 4 gauge or maybe bigger, maybe even 2. Wire's expensive. And as far as getting a 2 or a 4 gauge down a tube of the trolling motor shaft, forget it. It ain't gonna happen. Just not enough room in there. And then if you include, transducers in the newer ones and stuff like that, there's a lot of wiring going down there. So that's why they've done different voltage, because as you increase the voltage, the current effectively goes down. So you go to 36 volt, trolling motor, 101 pound. Let's say, I don't know for sure, I'm just making this up in my head. Let's say on high power, it's only pulling, 30 amps, or maybe even only 25 amps. I don't know the exact numbers, I haven't looked at the specs, but so you could get away with the standard wiring that is in the boat already, because 36 volts, you're not pulling quite the amount of current. So that's kind of why manufacturers, the higher thrust, that's why they increase the voltage. It has a lot to do with the current that it'll pull. The higher the voltage you go, the less current that the trolling motor is going to pull. And that doesn't mean it's going to last any longer. We talked about 3 batteries in series, and that it still equals 100 amp hour of the three batteries. Your amp hours don't go up. That's part of the reason. I mean, technically, a 36 volt trolling motors, Anyway, that's just how it works. One way a good comparison is think about the high voltage lines coming to your house. You ever wonder why, when you're driving down the road, those wires supplying, now although it's AC, same theory applies, they can have little bitty copper wires, it's probably about as big as this thing here, and they can supply a whole neighborhood, with, out on the power pole. That's because they're running, say, 8,000 volts or whatever it be. I can't remember off the top of my head what it is, 2,500 volts. Or even high tension lines, could be upwards of, hundreds of thousands of volts. And so the higher the voltage you go, the less current. Now once they convert it, if you notice that transformer on your pole that's supplying your house or whatever, you'll notice that those little lines are coming in the transformer, and it's stepping it down to 120, 240 on, different legs. But anyway, and those cables coming to your house are a lot bigger. Well, our voltage dropped, because we don't want 8,000, 10,000 volts coming into our house. So they step that voltage down, thus the cable size gets bigger. They go to like an aught size cable that comes into your house. So that's kind of the theory behind, why manufacturers go up in voltage. Has a lot to do with the wire size. They're really limited on what size gauge they can get through. Plus, the cost of copper these days is very expensive. It'd be expensive trolling motor, and 4 or 2 gauge or bigger, that's not cheap wire. That's expensive. Copper's expensive today, so. And then who knows, if we, started putting that in our boats, we'd probably have copper thieves coming and stealing the copper out of our boats. But anyway, I thought I'd cover that real quick for you, why that is, So anyway.